Can you hear me? No? Or yes?
Okay. So, welcome back. Today we again have several very interesting talks. Professor Marina Meilă will continue with her tutorial on clustering.
Thank you. The first poll of the day. How many of you had fun with Sandwich last night? Can you hear me? No. Okay. Can we turn this on? Well, of course you remember all this, right?
Can you speak now?
Good morning.
Can you hear? Better?
Apparently no.
Can you check? Is it working?
It's working?
It's at maximum volume.
Let's try again. Can you hear me? Okay. So, by the way, this slide wasn't in the slides yesterday, but it is now. And Vichy has received, as of 10 minutes ago, has received my new slides. So they should be soon, if not now, on the web, if you want to follow the slides on the web or download them. So this is where we stopped last time, with a list of theoretical computer science algorithms to estimate mixture densities, each of them with a new and different idea. And we are discussing how they have theoretical guarantees, but the requirements are very strong. So the guarantees do not kick in until the separation is large enough, unreasonably large, if you actually look, or unreasonably large in view of other results that I'm going to talk about today. Also, unreasonably large in view of this requirement that the algorithms impose on themselves without actually needing it, that we need to classify all the points perfectly. I must say that there is yet another algorithm that I mentioned briefly, and for which there will be a slides very soon, which doesn't make this assumption. But before that, I wanted to put up a very, very important result, which originates actually in theoretical computer science, which is used in some of these proofs. But it is much more far-reaching than clustering. It's hard to do anything in high-dimensional geometrical parts of computer science, and they seem to be, they are growing, the work on computer science in multidimensional real-value data, without using these results, which is the Johnson-Lindenstrauss lemma. And here is the original text of the lemma. It's a bit convolved and long. It says that for any epsilon I care to choose, and for any set of n vectors in high dimensions, no matter how high the dimension, I can project down to a d prime, a dimension d prime, which is actually not very small, which is logarithm of n times epsilon squared over 2, or slightly smaller than that. There is a typo. This should be greater or equal. So I need to project to at least this many dimensions, not at most as many dimensions. Yes. And if I do that, if I project the vectors on, so for any dimension larger than this lower bound, the Johnson-Lindenstrauss lemma says you can find a function that maps the vectors into the lower dimension without changing their length too much. In fact, by this much epsilon. So f of u is the mapping function. What can be proved, and this was the proof I have seen. There have been many alternative proofs to the Johnson-Lindenstrauss lemma. But the one I have seen, oops, I want to give credit to this guy. So this is I'll fix them tomorrow. There is a problem with BibTeX on this computer. OK, so this paper, called An Elementary Proof of the Johnson-Lindenstrauss Lemma, shows that, in fact, this F is nothing complicated. This F can be a random projection. So if you do a random projection of the data, random projection means you pick a random subspace of dimension d prime and project all the data on it. If you do that with high probability, probability greater than probability of failure smaller than 1 over n, you succeed in finding this mapping. So if you want for any probability, you can have just to repeat the process a few times to get it down to practically any probability. So it's a very fast algorithm to obtain this projection. Note also, what is interesting, as I said, is that the dimension on which you have to project does not depend on the original dimension of the data. It depends on how many lengths you want to preserve. Yes, because the trick is that when you project a vector, the vector is either almost orthogonal, like just simplify. It's either almost orthogonal to what you're projecting on, and in that case, the length is changed very much, or it's almost parallel, in which case the length is not changed very much. And this says that if I have enough dimensions, there will be enough, there will be enough dimensions so that the vectors will be, the subspace will be parallel with high probability with all the vectors. Yeah. OK. And the proof is elementary, and I want to show you part of the proof, or at least the beginning of the proof, because that's also an interesting result, and it's a model of probabilistic proofs in computer science. They are saying, I want to project a fixed vector, one of the vectors given, on a random subspace. Well, that's the same as fixing the random subspace and making the vector random. So I pick a vector randomly in Rd uniformly. That means that V is equal to V1 to Vd. D is greater than ID prime. And Vj, the dimensions, are IID from some distribution. Doesn't matter what. Yes, because I only care about the direction to be random. And I may also want to say that, no, I don't even care about that. Yes? Then what is the expected length? Expected length. And so projection, V tilde is projection. Projection of V. And since I have fixed the subspace, let's say I fix the subspace to be the first d prime coordinates. On E1 to E sub d prime. Well, the projection of V on the first d prime coordinates is equal to V1 V d prime 0, 0, 0. Yeah. What's the length? The length of the V tilde squared is V1 squared plus V d prime squared. What's the length of V? It's the length sum of all of them. Yeah? What's the expected length? And let's say we could make this 1, but let's not even worry about this. But you can think of this as being 1. So this would be shorter. What's the expected length of the projection? It's expectation of sum of Vj squared, j from 1 to d prime. And because these are identically distributed variables, the expectation of the sum is the sum of the expectations. So it's equal to d prime variance or expectation of Vj squared, E of V1 squared. Yeah? And this one also has an OK, and now I fix this to be 1. No, in fact, I don't even have to fix it to B1. By the same token, this is D equal expectation of V1 squared. And so expectation of V tilde squared the length is D prime over D expectation of V squared. So this says that, and then I can force this to be fixed. I can say all these vectors have fixed unit length, or I can leave it as it is. It's fine. This just says that in expectation, any vector is compressed by D prime over D, which means that if I want to preserve the lengths, I have to multiply. So what I said, F is not a random projection, it's a random projection multiplied by D over D prime, a scalar that we know. Yes? The second part of the result, which is slightly more difficult, is to show that actually the actual length, this is very close to the expectation always. You had a question?
Yeah. How did you get that the expectation of the sum is equal to D prime times expectation of just V1?
Because they are identically distributed. I picked them all from some distribution. Yeah, that's why. Okay. Yes. So the first result is that it's very simple. It's just the expectation is, we know what the expectation should be for the square length. Yeah. And then the second part of the result is, which I'm not going to show, is well, the variation of the length around its expectation is very small. And that's sort of a form of a law of large number results. If D prime is large enough, it means that I have a sum of D prime random variables. And so we have to prove something about the variance of the sum when we know the variance of well, this is the expectation, but when we know the variance of only one component of the sum. And we can show that that's one reason D prime has to be large, so that we can have concentration results on the variance. Okay. This appears in many, many places. For instance, the Johnson-Lindner-Strauss lemma is an ingredient in another area of statistics, or I don't even know if I should call it computer science or statistics or machine learning. That's called compressed sensing, which deals with sparse recovery. And you may, there is no lecture on compressed sensing here, but you may hear it from maybe Dale Schurman's, Professor Schurman's later, or others, which is sort of completely different from clustering. Also, it has, it appears in areas which have to do with graph embedding, where we have distances, but we don't know the coordinates of the points. And actually, the points don't have to necessarily come from a high dimension, don't have to be real vectors, but we have distances in some way. So that's called graph embedding. And the question is, can we find a subspace where the points have coordinates without distorting the lengths too much? Now, yes?
I think in the theorem, it should be a lower bound on the dimension.
Yes. Yeah, D prime should be greater or equal. OK, so this is a two-step algorithm, again, by Dasgupta and Schurman this time. Okay. And this is yet another idea. Does not use the Johnson-Lindner-Strauss lemma, but does the following. And when I'm going to go through the steps of the algorithm, remark that steps 1 to 6 are initialization, and step 7 is running EM. So the question they asked was, we know that EM, well, I have not told you, because I do not think it's significant, but EM converges as a gradient algorithm. So EM converges to a local optimum, not in a finite number of steps, asymptotically, but it has the rate of convergence of a gradient algorithm, which means that it's linear convergence. Now, in optimization, how many of you have had some optimization? OK. In optimization, linear speed of convergence, which means exponential decrease of error, is considered slow. It's sort of looked down upon. You want something faster. And so EM is traditionally considered, from this point of view, EM is considered slow. I will argue that in statistics, we don't care so much about this, because we care much more how much time we spend on an iteration. And also, I asked last time, in relation to EM, why don't we need to maximize always? What's good about not maximizing perfectly at every step? In fact, there is an argument in statistics for not maximizing perfectly even at the last step of an algorithm. And has anybody thought of the reason? OK, the reason is statistical. In optimization, the tolerance of the solution is expected to be 10 to the minus 8 or so, or lower. Yes. In statistics, the tolerance of the solution is given in statistical terms. We know that whatever we are estimating are not the true parameters. They are parameters from a sample. And in the case that, in the parametric case that EM is in, and or the mixtures are in, even the perfect solution on the sample will be square root of n, inverse square root of n from the true solution on average. Yes? So there's no point in taking putting a tolerance of 10 to the minus 8 if n is only 10 to the 4th. The tolerance we will have will be 1% on average, the statistical tolerance. Yes? And Dasgupta and Schulman exploited this observation. They said, well, everybody knows about the asymptotic rate, talks about the asymptotic rate of EM. But in truth, the hard part of EM and of many optimization algorithms is the transitory regime before you get to the asymptotic part. And that has to do with the initialization. And that is actually much harder to study even in optimization. Had a question? No? OK. So steps 1 to 6 are about the initialization. Step 7 is running the EM, and they show that it's sufficient to run it for one step if you initialize correctly. And this is the algorithm you've seen before under the name of power initialization. I put more detail in it. They assume that you have k-spherical Gaussians that are sufficiently separated. Sufficient means that I have this constant c, which has to be sufficiently large, and sufficient is this large. So it grows with dimension. And what is square root of d sigma k? If you have a Gaussian in d dimension, and it's spherical, so you have sigma on each coordinate, then the radius of the Gaussian, that's the radius of the sphere, of the sigma sphere, is, of the Gaussian is square root of d sigma. It's the length of a segment that is sigma on each coordinate. So this is the natural unit length inside this Gaussian. And with respect to that, relative to that, we have this constant c. OK, so the first step is pick O of k log k centers at random from the data. And I'm repeating something that I told you before with a little bit more detail. Set the there is a recipe for setting the sigmas so that they are in relation to the centers. We start with equal probabilities for each cluster. And then we run one step of EM. They need all these details for the proof. Whereas in general, the general case, you have no proof, so you don't need all the details. Yeah? Then we prune all the clusters that have too little data. Notice that each cluster starts with 1 over k prime. So this is a quarter of the average size. Okay. And then we run fastest first traversal, which means we always keep taking the furthest away point. But not with the natural, not with the Euclidean distances, but with these rescale distances, which rescale by the sigmas. And then after After we are done, we keep these k centers and run EM again. And one more, so the proof for the first 6 steps is that after you do this, you are going to have a center in each Gaussian. And in addition, if you look at the partial assignments towards those centers, most points will be assigned with high probability to only one center, the one of the Gaussian that they come from. So they prove that with high probability that there will be a vanishing fraction of points which will have partial assignments. Therefore, if you do one more step, you get to the means of the clusters. Yes? And this is what the result says, that the distance between what you estimate, so this is mu k is mu2, and the true means is, well, it can't be better than the distance from the means of the clusters, because you don't have the true distribution, you have just the means of the clusters. So this is the best we can do, take the mean of the true cluster. And it's better by epsilon times the scaling, the natural distance unit in that Gaussian. So it's remarkably good. It's very good. Yes?
In application, is there any k or range of k that this works better for? Like, there's a very small k this doesn't really work for?
This assumes that you know k. And later, possibly today, probably today, we'll talk about what you do when you don't know k. But here you pretend that you know what the true k is. Also, this depends on having high dimensions and separated Gaussians. So it may not work so well if the dimension is not so high, because it exploits concentration of density in high dimensions. Also, in the real experiment, in the real data, because you're not sure you have Gaussians, you may run EM more than once. Yes, so you don't have to stop after the first. Yes.
When you say high dimensions, you're talking about
hundreds. Yes. Yeah, very high. And to be realistic, in high dimensions, it's hard to find spherical Gaussians. Yes, only if the dimensions are just noise. Then you can hope the noise is the same on all dimensions. But OK, so results like this have been, so the other theorems assume elongated Gaussians and so on. So this is not a huge hurdle. But as I said, these theorems don't refer to real data. They are referred to pretty much almost ideal situations. However, they may work well in real data, and we'll see an example where actually this procedure, although the separation was much smaller than prescribed, worked very well. OK. Also, as I want to stress again, that there are very different regimes in which we do clusterings. So sometimes the Gaussians are separated in high dimensions, and then this works. But sometimes the Gaussians are overlapping, and then something else works, because then centers can transfer from one cluster to the other. So this is just one proof technique. It's not the only reason why EM should work. And another lesson to take from this algorithm is the following, that EM really is a finishing step. It's not EM that's doing the work. The clustering is actually, in the interesting cases, for clustering is a combinatorial problem. So this part is solving the combinatorial problem by a randomized algorithm. And that's how we should look at clustering. It's very much a game of initialization. And then we finish up with a nice EM algorithm that converges somewhere. But the hard work is done in the initialization. I want to finish the chapter on EM with an experimental exploration. This experimental exploration is done in a very simple case. And in the end, or maybe after the fact, the results won't be so surprising. However, it is important that it has been done, because it confirms things that we may have expected and confirms them in a quantitative way by experiments. So Srebro, Shaknarovich, and Roweiss said, let's experiment with EM in a very controlled way. So they took data in high dimensions, literally hundreds of dimensions. They created spherical Gaussians with centers on the corners of a hypercube, which means that the minimum distance between two centers is the same for all centers. And k was large, well, was going between 2 or 3 to 30 or 32 or so. So k was in a larger range. And variable separation. They tried various versions of EM. Because we are in high dimensions, we can do projection on a oops, there's a typo there. That should be a parenthesis. Yeah? So they could do the principal component projection that I talked about last time. They did the power initialization, the initialization that I described on the previous slide. And they showed that these actually improve performance. So they're worth keeping even in real situations. And let's see what were the results. So the most important is the top slide. On the top slide, you see first that k was 16, dimensions 512, and separation 4. So there are 4 sigma between the two centers. Sigma is the same in all dimensions and for all clusters. And they run 3 types of algorithms. The blue, the fair EM, is just run EM with the initialization that I described. The red is EM, but starting with the true centers. So this is cheating. It's not fair. But they wanted to see what advantage you have if you do that. And the green is I don't even run EM. I put the true centers in there, and I estimate the likelihood, and I label the data. And in this case, what we see first, and label error means how many labels were wrong compared to the true model. Now at separation 4 sigma, some labels will be wrong, but not many. Yes, it's 2 sigma. So separation 6 sigma means 3 sigma away, like the middle is 3 sigma away from each center. So you expect very few labels to be wrong, almost none. But 4 sigma, it's 2 sigma away at most for each center. And so you expect some labels to be wrong, and that's what we see with the green. That almost 5%. And this reminds you of the confidence interval, 95% confidence interval at just above 2 sigma, really. So about 5% are wrong. If you put the true centers and do some estimation, you're right too, except in this region where actually you do a bit worse. And actually, that's funny. I don't know why they do that. We'll see why they do that. And here on the x-axis is the sample size from 100 to 10,000. And what they saw is that no matter what the method, if you have enough data, by this initialization, you are going to find the likelihood is the same. So basically, they find estimate the true parameters and find the true cluster assignment in the limit of large data, which is nice. And this says something about the initialization. Because even if you have infinite data, the likelihood function will still have local optima. It will happen that the local optimum that corresponds to the true model will be higher and broader. And what you care about is not how high, it's how high enough. But you care about how broad, how large the domain of attraction. So the maximum corresponding to the true model is larger and more salient, but you still have local optima. So this says something good about the initialization. But with fewer data, and fewer means 1,000, you don't find the EM doesn't, well, 0.1 error is not so big. But basically, stays something else, somewhere else. Whereas the true centers actually have better error. Now, what is the pig? Pink is the maximum likelihood, marks the model that has the maximum likelihood of these 3, between these 3. So the pink, if we track the pink goes with the solution of EM. And this says that for little data, for few data, and few is actually up to where the pink switches sides, EM finds a more likely solution than the true solution. This means that I don't have enough data to point me to the true clustering. So the clustering that I find, I can call it meaningless, because it has no bearing to the origin, or very little bearing to the original solution, original model. Yes. So really here I have too little data to estimate the model. Here the maximum likelihood switches, which means that I have enough data to point to the true model, but EM doesn't find it for a while. What's interesting is that the question is it that the true model is still bad? No, the true model is not still bad, because if I start with the true centers, I actually do find the maximum likelihood solution. And they call these the computational limit and the informational limit. So here, I'm below the informational limit. I don't have enough information to estimate my model, to get to my model. Here, I'm above the informational limit because actually my model is more likely than what EM finds. However, EM cannot find it. And so they say that I'm below the computational limit. So a simple EM won't find it, but the solution exists. It's there in the data. So maybe some other clever algorithm could find it. Yes. And here we are above the computational limit. It means we have enough data that the algorithm we try, EM, does find the solution. This says something about the problem of clustering, and this was actually the reason why they did the experiment. It is one of the interesting outcomes of the experiment. We have clustering. This is a problem, it's given. But how hard the problem is it? Maybe it's always hard. Maybe and that's an hypothesis. Maybe, optimizing many of these criteria is intractable. Not always NP-hard, but intractable. Polynomial of high degree or exponential. So do we always have to find, is it hopeless from the theoretical point of view? Is it always a hard problem? And the answer is that it's actually not it's surely not always an easy problem, but it's also not always a hard problem. Sometimes it is an interesting problem. So a problem which is either too easy or too hard is uninteresting, yes? Either the easy algorithm works or nothing works. OK, we do what we can and we stop studying it because there's nothing interesting there. It's not true about clustering. We should do more research about clustering because there is this regime where there is a solution in the data and we don't know how to find it. Yes? I suppose it was, why did it rise? Like here. I suppose it was sample noise. So basically, the sample is large enough to tell you. So this is the figure I showed. Yes, the sample is large enough to give you the correct labeling and that the correct model starts becoming more important, but it's not enough to label all the centers correctly at 4 sigma separation. So it's label noise. Yes. So basically, these red centers are away from the green centers. Yes. So they move a little during EM. That's why. So they don't estimate so well until the data sample, the sample size grows, increases. Other questions? OK, so this is the picture for different separations. This is the 6 sigma. Here the transition is much more sudden, from not enough data to estimate the model to interesting enough data to estimate the model, but EM still doesn't find it. Yeah. Which means that as the problem, so this is supposed to be an easy problem, right? Very, very large separation. This shows that the combinatorics is the hurdle here. Yes. Because if I start from the true clusters, I do extremely well. But if I don't, then I need a lot of data to do. Yes? And here in the separation 3 sigma, this is almost overlapping clusters. And you see the transition is very narrow because there is a lot of overlap already. OK? Now there are other things that come out of this experiment, because it was done so many times and for so many values of the parameters. And this is a plot. So this is a summary of the theoretical results, the papers that you have already seen. And this is a plot of sample size versus k at different separation. And it plots the two transitions. So the blue, the informational limit, is where EM, the fair EM, starts finding the true model. No, the green, the computational limit, is where the fair EM starts finding the true model. And the informational limit is where the EM that starts from the centers finds the correct labeling, yeah? Which is at a smaller n. So if we go back, the computational limit is here. And at a lower end, we have the informational limit where the maximum likelihood points to the true solution. And the scale is double exponential, which means that, so these are almost linear at a doubly exponential scale, which means that n is a polynomial of k. It's k to some power along these lines. Yeah?
I don't quite understand why in the previous slide, when we're doing this constant likelihood, this drop is so sudden. Basically, we add 1 point and suddenly some 2 or like this.
Can you repeat the question?
In the previous slide, we covered like transition with number of points of the maximum likelihood, the purple one, the purple color, is too sudden. It's like drops immediately. Right? Basically, we add a couple of points and we already have the good result on the previous slide, right?
Right, and so why is the transition so sudden?
Yeah.
This happens very often with large samples.
Basically, 10 points can change everything for this year. So you increase a little bit number of points and suddenly you have good results.
Yes, and that happens. That happens often. Like there are these transition phenomena in many, like in 3-sat or so. You have also transitions. You add a few more constraints, and suddenly it becomes from infeasible, it becomes feasible, sort of from satisfiable, it becomes insatisfiable, and so on. And, so the question was, because it's an interesting question, I have to think of an answer. The question was, why is the transition so sudden? Actually, the transition is sudden if you look at exponential scale. So basically, let's say you multiply the sample size by a little bit, and it transitions. But it is a sudden transition, yes.
Maybe it's like it's easier to generate more data or something.
So this is the best answer I can come up with. I don't know if this is the correct answer, but the possibility is that if you look at concentration inequalities of all sorts of kinds, they have exponential bounds in the right side. And the exponentials behave like that. For a while, they're large, and then suddenly they drop. And it is possible that what we observe is a phenomenon. Oh, actually, it is. It's the sort of how concentrated is the data around, or how well does the data represent the true model. That governs the informational limit here. And so if the concentration inequalities are bounds, so they are not exactly what the data does, but those bounds actually fall exponentially usually. And so it is natural with n. So it is not so unexpected that if you look on a log plot of n to see a very sudden transition from the point where the data doesn't represent the true model to the point where the data does represent the true model. It's a possibility. I'm not 100% sure that this is the only explanation or the best explanation for this. Other questions? OK. So what they showed is that the sample size grows about linearly with k. And that's not always true in these from these results. Also, what's not shown here is that OK, the informational limit here can be calculated for every separation. It's much lower than what, so the separations where the informational limit occurs and the separation where the computational limit occurs for a given n and k are much lower than what's given in these theorems. Which also say we still have some way to go. There is a gap between the theory and what we observe in practice. Okay, and they do some more calculations which show that they are asymptotically lower, not by a constant. They grow at a different rate. That is what's more important. OK, let me see if you have more questions, because we are changing the chapter. So the next section is called issues in parametric clustering, but we talked about issues for a long time. So let's see what's left. The most important thing that's left is to select the number of clusters. So far we talked about knowing the number of clusters, and that's because the algorithms are set up so that they require it. But in reality, we don't know how many clusters are in the data. We may know a range. We may know that there are no more than 100 clusters. Or we may know that there are not 2 clusters, but at least 5. That's about all we know. So we know a k-min and a k-max. And what is done is something very simple, at least on the surface. We estimate a clustering for every k. And then we try to choose which one is the best. Notice one thing. The first, so the question is, how do you choose what's the best? And of course, you can think of, every clustering has a cost. If it's cost-based, then there is that cost L that I defined. If it's model-based, then the likelihood is the cost. And that's what we used to opt to find the k clusterings in first place. That cost cannot be used to distinguish between k's. And probably you already know why. Because if I give myself one more clusters, it means I give myself more degrees of freedom, and I'm going to decrease the cost. So pick any cost you want. Start with single linkage. If I give myself one more cluster, it means I remove one more edge. Definitely the cost will be lower. There's no way I can increase the cost unless I have a really poor algorithm if I increase k. Yes. So the cost, if my clusterings are any good, the cost is bound to decrease. So it's not a good, it's always going to decrease. It's predictable. It can't predict k. So we have to come up with different methods for choosing k. And now it depends whether we do model-based clustering or cost-based clustering. For model-based clustering, we can use the fact that we have a probabilistic model and use model selection techniques that are verified from statistics and apply to this. And one model that is, in some sense, best is BIC, which is the Bayesian information criterion. Don't ask me why it's called, well, you can ask me why it's called Bayesian. But it's not very relevant. OK? And that says the following. If I give myself more degrees of freedom, so I have more parameters, then I have to somehow penalize. Then I'm going to increase the likelihood. This is L is the log likelihood. Yeah. I'm guaranteed to increase the log likelihood. So I have to put a penalty on the number of parameters. And the right penalty, they say, is the number of parameters times logarithm of the data. So the more data I fit with the same number of parameters, the higher the penalty, but only by a logarithmic factor. OK? And so if I do this, if I penalize the likelihood by something that's an increasing function of the number of parameters, I expect that the function may not be monotonic, and indeed it's not. It starts decreasing after a while. And it will look like here. Yes. So this is the example of real data flow cytometry biology data. And these are clusterings by all the variants of covariance structure that could 8 possible, or more than 8, 10 variants of possible shared parameters to structures. BIC is plotted. You can't see the numbers. I can't see them either, but they're not important. So here is the number of clusters. And here for each method, a clustering has been done for every k, and the BIC is plotted. A is the number that's too restrictive, has all parameters are shared, so the likelihood is lower. And this is typical for BIC curves. They grow very fast here because the likelihood grows very fast. Log n is the same on all the spots. And then they plateau, and then slowly will decrease, like this, yeah, outside. In fact, by here they already decrease because the maximum is at k equal 8. Notice also that in addition to being able to compare models with different k's but coming from the same mixture model, BIC allows to compare between different model classes. So it is OK to compare model A with model J using BIC, as long as they are fit on the same data. So that's an advantage of BIC. It's universal from this point of view. Yeah. So this is an example. So the question is, why is this shape concave? It's not provably concave, first of all. But that's what we observe. And it's because it's the difference of two increasing functions. So the likelihood is increasing, and the other term is increasing, but I subtract it. OK? And the other term is linear. OK. And so here, the likelihood is increasing very fast because I add degrees of freedom that are useful. After I stop adding degrees of freedom that are useful, any degrees of, apparently, for a while at least, the increase of likelihood seems to be, of the log likelihood seems to be linear. And that seems somehow natural. I'm not going to go into the details. And after that, more degrees of freedom probably don't do a lot, and you're going to see a fall. The other slope is much more gentle, always. OK. So what I want to see about BIC. Theoretically speaking, there are some conditions under which, so there are some technical conditions under which BIC works, which means that there are some technical conditions which could appear for mixtures when it doesn't work, having to do with the parameters of the true model. But in practice, it appears to work pretty well. So there are people who swear by it. Anyway, you should know that it's not guaranteed to work. However, for instance, if the parameters are in the compact set, and if you know this from your data somehow, that your parameters will have to be in a compact set, then it is guaranteed in the limit of infinite data to select the true model. And it is guaranteed also to select the best model in the limit of number of data. So the problem is that it does require, but otherwise, if you looked at the proof for BIC, it's a very crude approximation. So if you have enough data where enough depends on the data set, and you don't know when it's enough, then BIC is the thing to do. It may not be enough for lower sample sizes, and again, I can't tell you when it's not enough. And in that case, it tends to underestimate the number of parameters, to be slightly too conservative. Okay. By the way, there is also something called AIC. How many of you have heard of AIC? Oh, so many. Actually, you've heard it in here yesterday. So AIC is BIC without the log n. So it's L of theta minus this tends to overestimate the number of parameters. And this takes it very vaguely on typical data sets of some kind, which may be clustering. Yes? OK. For hard clustering, so you have only heuristics. Only heuristic methods, which means we have no proofs for them. They're just tested in practice. The first one, which is actually, from a statistical point of view, the best one I know, is called the gap statistics. It comes from some statisticians. Every step is statistically sound, but it has no proof that it's correct. The idea is as follows. I'm going to use the cost. But just like BIC penalizes the cost by the number of parameters, here I'm going to penalize the cost by looking at the relative cost between my data set, where I'm supposed to have clusters, and the data set that has no clusters, which is sort of like the null hypothesis. So I'm going to choose some null distribution. So suppose my data is in the interval 0, 1, and is clustered. I'm going to choose uniform over 0, 1 as the null distribution. Now, usually my data is not in 0, 1. My data is probably in high dimensions and in some very large intervals, and has outliers, so the interval is even larger. So choosing the null distribution is subtle, and you see 3 possibilities. It means that none of them is a real winner, so you have to think what's the best for your data. So one possibility is to put a Gaussian distribution, because the data will have sort of tails too, a single Gaussian with the same variance as the data. Another possibility is to say, well, the data is in high dimensions. Usually in high dimensions, data lie on a subspace. So it's not good to put a Gaussian on of the same dimension as the subspace. Find the principal subspace and fit a Gaussian to that. So basically, think of the best distribution that matches the data in some criteria, is close to the data but has no clusters, as your null distribution. And then compute the expected cost under this distribution with the same sample. So this is what the cost would be if I had no clusters. And then the gap is just the difference. The cost will be larger if I have no clusters. Therefore, this is always hopefully positive. And the gap tells me how good my clustering is, how different from a no clusters distribution. Okay. Then K star is what goes to the larger gap. End of story. Actually, it's not the end of the story, you'll see. Because if you do it this way, it doesn't work well when you know what the clustering is, what the clusters are. But one thing that's nice is that if you have no clusters in the data, you find this out. Nothing is better than a null distribution. It means that you shouldn't be looking for clusters. OK. There are some practical issues, for instance, that you have to sample to obtain the expectation, because usually you can't compute it analytically. If you sample to obtain the expectation, it means that whatever the L0 that you get has a variance. That's not such a problem, because statistical testing knows how to deal with this. You sort of apply some statistical testing theory and find how to compare a constant with a value that has a variance, and what's a significant difference and what's not. And here is a recipe that they use. Take 1 sigma distance. And this is a criterion that they seem to say that it works well. The problem is that it doesn't work, it's not 100% guaranteed. It's a heuristic, and if you tweak it well for your data, it will find something that's close to the number of clusters. If you don't, it will give you something different. And a good indicator of when this is true is when the papers have a lot of variance of the algorithm. If you have an algorithm that solves multiple problems, you can have variance. That's a good algorithm. If you have an algorithm that is trying to solve a single problem and has 10 variants in the same paper, it means that none of them really worked well, better than the others. So you are free to optimize it yourself. It is time to stop now. I will have a slightly more to say about these heuristics. And we'll do the other method of selecting K, which is also a heuristic, after the break. Let me see if you have questions now. No? OK. Then we have a break of half an hour, right? No? Well, we have a break anyway. Is it a long break or? The coffee break is at 10, so no half an hour? OK. All right, so then a 5-minute break. Feel free to ask questions.